Yeah, hello everyone, and welcome to this spring's Thomson lecture series. I'm happy to welcome Deanna Hence as our Thomson lecturer this spring. Deanna is an assistant professor at the Department of Atmospheric Sciences at the University of Illinois, and her research interests lie in high-impact mesoscale and synoptic scale weather phenomena, precipitation processes, and cloud dynamics. But her heart also lies with science communication, risk communication, policy, and outreach. Before becoming a professor at the University of Illinois, Deanna was a postdoctoral fellow at NASA Goddard in DC, and before that, she received a PhD from the University of Washington, working with Bob House. And before going to grad school, she got a bachelor degree from the University of Michigan in 2004. Now, Deanna is not a stranger to NCAR, and she actually worked here for 2 or 3 summers as a source protege, I think in 2003 and 2004, where she worked with Wenxiao Li and Michael Bell. So welcome back, Deanna. It's been over 10 years, I guess. And her talk is about remote sensing multiscale interactions of tropical convection.
Thank you so much, Falco. Yeah, it's just actually realizing that this is the first time I've been on this stage since I gave my last SOARS talk in 2004, so it's 13 years ago. Oh, God. But today, so this is going to be a pretty broad talk. So I'm happy to talk about any of the more details of this work, offline. And I wanted to do this in the form of a story of how I kind of stumbled into this realm of looking at tropical convection through a remote sensing perspective. And so I want to acknowledge Jeff Thayer, who's my current master's student. So I'll be presenting a lot of his work. And then also Scott Brown, who was my postdoc mentor. Because the work that I'm going to be presenting is going to be a combination of how I stumbled into this as a graduate student, moving through my postdoc, and now what I'm doing at the University of Illinois. So I wanted to start off with this image because, as you can see, this is the central Indian Ocean, or it's the Indian Ocean basin overall. So here's India, what's at the eastern coast of Africa. And I wanted to show this is because what you're seeing is a large complex of clouds over the central Indian Ocean. This is associated with the Madden-Julian oscillation, otherwise known as the MJO. I just wanted to give this as an introduction to see what kind of scales we're going to be talking about here. So we have this large synoptic scale phenomenon associated with the MJO, but then we have a whole bunch of convective cloud clusters and systems embedded within this. And so as I kind of stumbled into this realm, I wanted to really start exploring how do these different scales interact with each other and really influence tropical precipitation systems. So to make more of a point of this, this is a loop of Hurricane Charley when it hit Tampa, Florida. And this is pretty typical hurricane. We have this large bands of precipitation spiraling around a high precipitation core. So we have this large vortex that is its own system on its own scale. This is on the very large end of what is considered to be the mesoscale. But then embedded within this, we have individual convective elements, and those individual convective elements are organized into these larger scale features. And so we have the large spiraling arms known as the rain band, embedded within those as individual convective cells. We also have that strong feature that comes back around here, coming along, there we go. We have the eye wall here, that band of very intense precipitation that is a feature of the secondary circulation of a tropical cyclone. So that's that in, up, and out flow that defines that eye wall cloud. So these are a lot of different convective processes happening on many, many different scales, both individually, but then organized into this larger system. If we go even bigger than that, though, this is a satellite loop again of the Indian Ocean basin. And as we're going through, you can see the convection associated with the intertropical convergence zone, otherwise known as the ITCZ. But then you see this massive blow up of convection that occurs right in the center of the basin. And that box is kind of highlighting that region. This is that initiation of the Madden-Julian oscillation that happens over the central Indian Ocean. So now we're moving from the convective scale through the mesoscale, and now in this framework we're starting to talk about the synoptic scale. So how do these different scales of interaction influence these precipitation processes that are really going to be the product of the individual convective elements that are embedded in these systems? So I'm going to be telling this through what I consider kind of a personal story, because I didn't really go into my graduate work with the intention of doing tropical precipitation. It just kind of happened. But as often happens when you do a PhD, you sometimes start getting more questions than you're really answering, and this question has been driving my work as I've continued forward. And this question is, do these larger scale influences, these things that are happening on the synoptic scale, significantly influence precipitation production and evolution of these tropical convection systems on these smaller scales? And more importantly, and I think the bigger question is, if they do, how? This is going to be, I sometimes think about the scientific cleanup committee. I think there's a lot of inherent assumptions about what say dry air does or vertical wind shear does, but when you actually ask, but how does this impact the cloud? How does this impact the system? Suddenly things are much less clear. So this is the area that I'm hoping to delve into. And so when we're talking about something as large as a hurricane, for example, this large vortex feature, as I've talked about, we have all of these embedded features and embedded convective cells within that, all the way down to the individual feature itself. So what I'm going to be looking at primarily is this interaction here between the convective scale and the mesoscale. So this would be more on the mesoscale here, convective scale. But then I'm also going to be looking at how does the synoptic scale, these larger scale features, impact these things. Now, this does raise the question of, couldn't I make this arrow two ways as well? How does these mesoscale features and through the convective scale features through these mesoscale features impact the synoptic scale? That is an incredibly valid question, but I do need to sleep at night. So I'm not going to be able to address that one so much. I'm going to be more focusing from the larger scale downward. So how did I get in all this mess? So I constantly tell Wen Chao that all of this is his fault. And how this came to be is that when I was a SOAR student, I started here at the Earth Observation Laboratory. So I was running around at Foothills Lab and constantly harassing people. The benefit of being a part of SOARS was that I got experience working with the Doppler radar, otherwise known as Eldora. So then when I went into graduate school, Bob House, when I went to meet with him, he asked me, well, tell me about yourself. I was fishing for things to talk about. And I'm like, well, I worked with Eldora looking at hail formation. And he's like, wait, you've worked with Eldora? I'm like, yeah. And Bob gets his cogs working in his brain. He's like, well, I'm getting ready to take Eldora into hurricane environment. Are you interested? And I'm like, sure, why not, right? So as it turned out, Bob was planning the RainX field campaign at the time. And of course, this is one of those situations where, y'all know how field campaigns work. You plan them years in advance. You put them at the time where you think that the weather you want to study is most likely to happen, and you pray it actually happens and the weather actually cooperates. Now, as joked, I don't know did any of y'all go to the House Symposium? A couple people. People joke that Bob has had the most insane amount of luck when it comes to field campaigns imaginable. And it turned out that, of course, RainX was wildly successful, largely because Hurricane Katrina happened during the campaign. And we got amazing sampling from it. So this is a radar image of one of the sweep file of the Doppler radar through one of Katrina's rain bands. And so what you're seeing here is you're seeing this pretty homogeneous reflectivity associated with that kind of stratiform-like precipitation coming in the rain bands. But you also see these individual convective elements. So if we look at the radial velocity, if you think about, okay, the green is winds are going towards the radar, the yellows and reds are winds going away from the radar. So what you're seeing here is that you see this green, the green radial velocity suddenly changing to yellow here. That's a symbol of, convergence happening there. And you have the opposite happening aloft. That's a signal that you have this surface convergence, upper level divergence. So an up and out flow associated with that convective cell. And you're seeing that same heat on this side here. So I was flipping through all the radar images like, wow, this is happening a lot. That's interesting. And so if we mash all those various mappings of the rain band reflectivity together with the Eldora radar seen here in red, in the lower resolution, but still plenty fine, NOAA P3 radar, this is the teal flight track, we, for the first time, were able to fully map the reflectivity structure of a hurricane rain band. Because, and this is one point I like to make, this figure 4 sampling pattern that the NOAA P3s typically fly is not good for that. One big difference that RAINX accomplished that other campaigns did not is that this leg here that the NOAA P3 plane flew in conjunction with the flight path that Eldora was flying on the NRL P3 was a feature following flight. So we were able to fully map this portion of the rain band. Now, what we came out of this is work that I did, and also Anthony Didlake, who's also a former SOARS protege and is now faculty at Penn State. Between the two of us and doing dual Doppler analysis, we came up with this mapping of the various different kinematics through the hurricane rain band. And so I primarily focused on the updraft component, where we have this in, up, and outflow in these convective cells. You have the high reflectivity core associated with the rain falling out of this tilted outwards, updraft. And then we have this J is symbolizing a secondary horizontal wind maximum. And what we were finding was that this in, up, and out flow in this very highly sheared environment of the hurricane flow led to the development and strengthening of these secondary horizontal wind maxima. Anthony focused on the downdraft components, where there's a second wind maximum that also developed on the inner edge of the rain band through various processes as well. So one reason why I bring this up is because one thing that was in the literature prior to this study was that this assumption that rain bands are inherently bad for hurricanes. That these downdraft flows that are highlighted better in Anthony's work are bringing low theta E air, so low moisture air to the surface. Then the idea was that low moisture air was getting taken into the center of the storm and would weaken the storm. But one interesting consequence of this work is that, and this has been later borne out in later studies, is that actually one thing that this is doing by strengthening the winds further away from the storm center, you're broadening the potential impact of the storm because you're making the wind stronger at further radii. So this issue of focusing on just the center of the storm and where the eye of the storm is going to go becomes problematic when you start thinking about damage. So this was that first taste of like, there are some things here that I think we make inherent assumptions about that may not work out so well in reality. Now, another key component of this, and this was work that Anthony did later on, is looking at what I kind of consider the long ignored aspect of tropical cyclones, and that is the stratiform rain band regions. As a convection person, oftentimes we tend to focus on the strong convective cores, or in the case of the hurricane, the eye wall, where you're having this strong upward motion. But stratiform regions are often very, very dynamic regions, and because they operate much more on the mesoscale, they can, in large quantity, be bringing in these kind of rear inflow jets. So if you're kind of thinking like the Howe's squall line model, where you have these rear inflow jets into the trailing stratiform of a squall line, what Anthony was finding is that there's something similar happening in a hurricane. But if you're thinking about how large a hurricane is doing this on a massive scale, that can really start to influence the dynamics of the storm, again, much further afield and outside of the center of the storm. So if there's these things that we're kind of inherently overlooking because it's not, frankly, as exciting as looking at an intense convective cell, at least for, someone who looks at convection like me, right? So this issue of what's going on with stratiform precipitation, what assumptions are we making about stratiform that may be inherently, if not erroneous, in at least a very limited perspective? When it comes to tropical convection, this role of stratiform precipitation in terms of this connection between the convective scale all the way through to the mesoscale and synoptic scale starts becoming very, very important. So from that, I'm like, okay, enough with the case studies. I want to look at the bigger picture. So what I ended up doing was taking a look using the trim precipitation radar to try to do a statistical analysis of hurricanes and their precipitation distribution. So the great thing about TRIM and now GPM, that's its replacement, is that it gets very high resolution in the vertical. So its horizontal resolutions, it's not the best, but very, very detailed information in the vertical. So we have the hurricane eye wall, the various reflectivity signatures associated with the rain bands. Now this does not have particle information, does not have kinematics, but because of what we know from the previous case studies, then we can kind of take that knowledge that we've gleaned from studies of RainX and all the work that preceded that and pass that on into what we're seeing in the reflectivity structure here. So from that was born a lot of statistics. Got to reteach myself statistics for the third or fourth time when I was doing my PhD work. And this was something that was really interesting. And this, again, it was that, are we making some assumptions that may not necessarily bear out? This is the mean reflectivity structure. For what I did is I divided the storms into various categories based on their sea surface temperature, the amount of wind shear, their intensity, and some other factors. And then I also divided the storms into a series of rings based on their eye wall diameter. And from those statistics was able to determine, just from the statistics, not an arbitrary, well, this is inner core, this is not. What was the inner region, so the inner core region versus the distant rain band, outer rain band region. And this is showing for the sea surface temperature, where the blue is your marginal SST. So this was SSTs, I believe, between 26.5 to 28 degrees. I didn't have a large enough sample for low SST, so below 26, because of where TRIM operates. From 40 to 40 degrees latitude. And then the pink is your high SST. And so one thing that was really interesting that came out of this is that if you notice, for one, the difference between the inner and outer rain bands for the marginal SST values was very, very small. That was unexpected. The other thing that was unexpected, though, was that the reflectivity structure for your high SST values was not that much greater. It wasn't a very large difference. And if this panel here is what's called kurtosis. So if you don't remember that from stats class, that's that fourth moment about the mean, where it basically is a measure of how flat or how peaked your distribution is, and also how wide your tails of your distribution are. So this is normalized to 0. So usually it goes to a 3 is the transition point, but I took the 3 out, so that's where the 0 is. So when you get more negative, that's a flatter distribution with wider tails. More positive, that's a more peaked distribution with very narrow tails. So what you're seeing here, and this is the thing that was really interesting, the lower levels tends to be very flat distribution. Upper levels tends to be much more peaked, much more uniform. And this is something that also came out in the CFADs, or contoured frequency by altitude diagrams. This was basically a way to pull out the details from that analysis. But one thing that was interesting about this is that, again, the differences in the actual structure between these marginal SST cases versus the high SST cases were not as big as I was thinking they were going to be. So does that suggest then, especially since this analysis was done on mature storms, does that potentially suggest then that once a storm reaches a certain level of organization, that its impact of its environment is much more limited than when a storm is weaker and less organized? So what basically is that mesoscale organization? Could that possibly be protecting the storm in some way? So one thing that did come out quite strongly, however, was the impact of shear. So what this is the outer rainband reflectivity, mean reflectivity, and this is the inner rainband reflectivity. And so one of the main results that came out of this study was that when you hit these storms with shear, that really, really dramatically impacts the reflectivity, the precipitation distribution in a way that vastly outweighs any of the other things I looked at. So it was through this role of wind shear and its impact, because when you're talking about tropical convection, you don't really have much else to work with, right? The tropical atmosphere is relatively homogeneous. It has relatively constant, especially boundary layer moisture. It has very, very few temperature gradients. And so what are the things that are going to impact tropical convection? So that brings me to my postdoc work. So I spent some time at NASA, as Falco said, and my main purpose there was to be part of the Hurricane and Severe Storm Sentinel experiment, otherwise known as HS3. So this was a bit unique because this is my first time flying through a hurricane without actually being on the plane. These are high altitude drones. They're Global Hawk aircraft, usually used for reconnaissance by the military. NASA got a couple of them because the Air Force decided they didn't want them anymore. And the goal of these are planes that can stay in the air up to 25 hours. What that enables, you see that this is where they're flying out of, which is Wallops Island, Virginia. Because of that long time in the air, they also fly at 55,000 to 65,000 feet, so they're in the lower stratosphere. They could fly all the way to just off the coast of Africa, stay in the air still for 8 hours, and then fly back. That's something we haven't been able to do before, right? Having these extremely long sample times. One of the things that's always limiting aircraft missions is the amount of time you can stay in the air. So this is showing all the different missions that we flew into Hurricane Nadine back in 2012. I'm going to be focusing on, actually I'm only going to really focus on one of these flights, is this one here. And this was the time frame that Hurricane Nadine strengthened to a Category 1 hurricane. I'm also looking at this day as part of my research. This was the first flight that we did into her. But because of the sampling, I'm going to mostly focus on this one. This storm, I swear, challenges so many things about the basic assumptions of what we think affect hurricanes. Nadine was in okay, not great sea surface temperatures. Nadine was getting socked with shear on a regular basis, and Nadine was interacting with the Saharan air layer, that dry, dusty layer coming off of Africa. For every reason possible, Nadine should have died 1 million deaths and didn't. So I'm completely fascinated by what was special about Nadine. Why was she able to hold together when so many other storms fall apart? So just to give you an idea, this is Hurricane Nadine on the 11th and 12th. So this is a composite of MODIS imagery, aerosol optical depth. And so you can see here, this is the dust plume. This is the west coast of Africa here. So this is that dry, dusty air associated with the Saharan air layer. And you can see that on this day, it's all on this northeastern, eastern, northern side of the storm. So by that, one would think like, oh, well, Nadine's screwed, right? There's no way that she's going to be able to survive this interaction. And here's the reasons why people think this. So this is from the Dunyan and Marone study of 2008. And what their intent was to update what is known as the Jordan mean tropical sounding, which is this black line here. And try to update that for, okay, well, what does this sounding look like based on the various months in the tropical Atlantic Ocean, and at a time where you're dealing with non-Saharan air layer, so non-sal air, versus when you're dealing with sal air. So what you're hopefully seeing in these soundings is that, so this is the Jordan mean sounding here, this is it here. There's a dramatic shift in your mid-level moisture between the time you have sal air, so it's moister than that Jordan mean sounding, and versus when you have sal air, it's much, much drier. So as it turns out, that Jordan mean sounding is, well, exactly that. It's kind of an average between these very dry periods and these much moister periods. Now, one key thing, though, I want to point out about this, though, is that the sal itself is only this part here. That layer that's about between 700 and 850 hectopascals. Everything above that is not associated with the sal. And as it turns out, the reason why that is because when you have major sal outbreaks, it tends to correspond with times when you have very, very powerful Bermuda highs. So very strong subsiding air over the central Atlantic that is very, very dry. So you have this very dry, non-dusty layer overriding the dry, dusty air that's coming off of Africa. So I really wanted to look at, okay, what's going on with Nadine? Obviously, there's a sal outbreak, so it's probably got something like this going on. What's going on with all this? So if I look at, this is the NHC trace of Nadine's life cycle. Nadine, I think, is the 4th longest lived cyclone on record, if I'm not mistaken, in the Atlantic. Well, wait, yeah, in the Atlantic basin, I should correct that. But, you know, lasted a month, right, or darn near, right? So these red lines indicate the 2 days that those first 2 flights that we did into Hurricane Nadine. There were flights that happened in this period, but I'm not focusing on them. What I want to point out is that, as I just showed you, during both of these days, Nadine was interacting with the Saharan air layer, had all copious amounts of dry air. And yet, you notice what's going on during those 2 days. Nadine is not only holding together, Nadine's actually strengthening during that time frame. So what the heck's going on with this? You'll see that this is generally the theme of my research. What the heck is going on with this, right? So if we look at, this is the geopotential height map. So this is Nadine's center here, that little pink star. So you can see that really, really strong subtropical ridge, right? Hopefully, the other thing you're noticing is that, well, just like when you're going, winds that are going over a ridge, this is the 200 hectopascal map, those winds tend to be accelerating, right? That's kind of that curvature, you know, synoptic scale interaction. What does that mean? That means you have very, very high wind shear. This is the relative humidity at 850 hectopascals. No, 800, excuse me. So you can see that dry plume. Now this is a time where Nadine has moved further away from the coast, and so that dry plume is kind of starting to get thinner, roping out a little bit, but you can still see that there's a lot of dry air on Nadine's eastern and northern flank. But so we have this very dry air. We also have this very high wind shear resulting from this interaction with the upper portion of the ridge. So like I said, by every metric that we think about, Nadine should be dead, right? So we're going to look at this data from this particular flight. And one other thing I want to mention is that, yeah, there's no question that the high wind shear was impacting Nadine. This is a trim overpass of that particular time. You can see how asymmetric that Nadine's reflectivity structure is. So that's pretty typical, right? All the precipitation, what I was showing in that previous research I showed from my trim research, that all the, especially rain band precipitations being pushed downwind. That's very, very typical structure. But Nadine's still holding it together. So let's see. Let's look into this. So my first question was a very basic one. Is the Saharan air layer air mass, that very dry, dusty air, is it making it into the storm center? Because it's not going to do anything to the secondary circulation of the storm in terms of the eye wall if it can't make it in the first place. These are soundings. So this is the sounding, the relative humidity at 800 hectopascal for all of the dropsons that are dropped during this mission. So the nice thing about this mission is that we stayed up for a very long time. We basically flew this flight pattern that dropped a series of sons. Now you see that they're not in that perfect grid. It's because I allowed them to, they're showing where they actually took that measurement in terms of the location. So they, of course, sons get blown around, right, as they're falling. This pink line here indicates the storm's motion during the entire flight, right? So the storm, as you can see, is starting to recurve off towards the northeast. So what you're seeing here at 800 hectopascals, you see that indication of that dry air on the eastern and northern side of the storm. What you're not seeing is any of that being over here. So despite having all this dry air on this side, the storm center is still staying quite moist, which is very important for the storm circulation to stay healthy. Now, this image over here is also at 800 hectopascal. This is the radial wind component. So this basically is taking the dropson winds and removing the tangential wind component. So it's only showing the radial component. Might be a little hard to see, but what you're essentially seeing is that there's this cross-storm flow from south to north through this region. So generally speaking, there's, for what the component of the winds is going through, that source of air is still quite moist. It's coming from a much moister region than what's happening over on this side of the storm. Further evidence of this, what this is the scanning HIS, which is this is a measure of the relative humidity from the interferometer during those flight paths. Now, the thing about this instrument, and this one as well, this is the cloud physics LiDAR, is that they can't see through clouds. This is the one main limitation, and this was actually one of the frustrating things that we had about HS3, that unfortunately the plane that carried the radar refused to work this entire year. So we had to do what we could with what we had with the dropsons and scanning HIS and also CPL. But basically what this is showing, this is the chunk of the flight that these two images are showing. So at 0400 UTC, which corresponds with this time here and then to this time here, what you're seeing is that very, very deep layer of dry air. However, as you can see by what's on CPL, this is what dust looks like in the cloud physics LiDAR. This is dust associated with the south. You see that there's none of that over here. So this is very dry, very deep layer of dry air, but it's dust-free. So this air over here is most likely from that dry subsiding air from the Bermuda High. Now, if we look more forward in time, however, now we're over here. Now we're in that plume of Saharan air layer. And so what you're seeing here, now you're starting to get into the dust. It's a little hard to see on this scale, but there is also a bit of a drop in the relative humidity in this layer. Unfortunately, this is also in the rain band, right? So all those gaps that you're seeing here is it trying to see through cloud and not being able to. But you kind of see a hint of a drop of relative humidity in here. Now, one thing I also want to mention about scanning HIS is that its vertical resolution is not the best. And so in the Saharan air layer is only 150 hectopascals deep. So there is also that issue of some of that signal getting smeared across several gates as it's going towards the surface because it's not a very thick layer. CPL doesn't have that problem. And so one thing that was pretty great was that we had, of course, numerical modelers working with us, and they were able to do a successful simulation of Hurricane Nadine. And one thing that was great is that because anyway, that they were assimilating these observations into their simulations, they were actually able to accurately represent this humidity situation that was around Nadine. So you can see the plume of dry air in the simulation very closely aligns with what we see in the dropsondes. But you can also see that there's this plume of moist air that seems to be making it into the storm center pretty much unhindered. So I think this may be one of the keys to Nadine's survival. Now, the other thing that was interesting about this is that because now we have a completed wind field from the model, we were able to calculate some convergence fields. And one thing that was really interesting is that you had enhanced convergence here in the storm center, but on the inner side of that rain band. That's really important because if you see that enhanced convergence, inner side of the rain band, that's quite moist. On the other hand, you're having enhanced divergence on the outer edge of the rain band. So in essence, you're getting the enhanced divergence movement away from the storm center of the Saharan air layer, while there's plenty of convergence of moist air happening inside the storm. So this may be a hint as to why Nadine was still managed to hang together despite having everything going against her. But, and there's always a but, it's not that Nadine's life was perfect. So this is looking at the upper levels. This is up at 400 hectopascal. You see that there is plenty of dry air in the upper levels. And if we look at the radial wind components, now we have a cross-storm flow that's from west to east. So that's from that very, very dry air that's from the west blowing across the storm. So one thing that was interesting about Nadine is that her cloud depth was starting to become much more shallow and much more asymmetric as time went on, especially as the shear picked up more and more. So it wasn't that Nadine wasn't impacted. And in fact, after this time, Nadine leveled off in terms of intensification and eventually started to gradually weaken. So it's not like she wasn't being impacted. It just wasn't, it wasn't instant storm death. Like everything that we think would mean this is instant storm death, and it wasn't. So this has led to two key questions for me. And this is what's been driving much of the rest of my research. Exactly when and where is lack of moisture a problem? Is lack of moisture always a problem? Right? You would think, okay, clouds need moisture to hang together, should be a problem. It's like, well, is it always? Right? And then also, when and where is vertical shear a problem? Hurricanes, everyone says, like, they like low wind shear. It's like, well, that seems to be true for the most part, but is that always the case? Are there exceptions to that? So after literally right after I finished this, I defended my PhD, and a series of events happened that led me to ending up going on the Dynamo field campaign. And which was awesome. I mean, one of the best experiences of my life. I got to spend what ended up, it was supposed to start be 1 month, not over any holidays, ended up being 2 months over both Thanksgiving and Christmas and New Year's. So, but it was worth the effort. We were stationed on this on Adu Atoll for the campaign. So, people are like, oh, you got to be on the Maldives for 2 months. Woe is you. I'm like, well, in a windowless trailer, there's trade-offs, right? I told you that so much of my research is driven by what the heck is going on. This, literally, I started seeing this stuff on the radar. I'm like, what the heck is this? Especially this stuff. Now, this stuff looks familiar, right? That looks like a, pretty, like a, squall line like what we see in the United States. We have some isolated convective squalls, maybe some stuff trailing some stratiform. But it's this stuff in particular. I'm like, what the heck is that? I lovingly started calling it radar barf, because especially with the color scheme of SID, it kind of looked like that. But that brings us back to this question of what's going on in Central Indian Ocean. So I showed this loop before, but in this particular loop actually coincides in time with the particular time frame when we're looking at. This is the first MJO that was sampled by Dynamo. So this would have been October 15th through 31st or so. And so you can see the massive blowup of convection that happened in the central Indian Ocean, and you can start to see that convection blowup propagating off to the east as it made its way towards the Indian Ocean. And for those of you who are not terribly familiar with what the MJO is, this is the paper that basically, well, one of the papers that essentially gave it its name, Nadine and Julian in 1972, and this was the first, well, actually, it's disputed now whether it was actually the first. We actually just had someone at University of Illinois who challenged that notion, that maybe this was possibly identified earlier than this in China. I'll leave that controversy to other people. But if we look at the longitudes that are specific to the Indian Ocean, that's what these yellow lines show. What you see is that you have this initiation of convection in the central Indian Ocean, develops into deeper convection, and then it starts to propagate towards the east, off towards the maritime continent. And as that convective envelope moves off to the east, you get what is called, that convective envelope being called often the active phase. And if we just focus on this chunk here, because this is the part that primarily, I think, affects the Indian Ocean, we have this part being called the active phase. Then the thing that follows behind it being known as the suppressed phase, where you have predominantly subsiding air following behind it. Now, one part that's particularly interesting about it is that you have this chunk called the westerly wind burst, and this is that enhancement of low level, about 850 hectopascals, low level winds that accelerate just after the convective envelope moves on. And so if we look at this chunk here of a Wheeler and Hendon, the phase space of the MJO, this red chunk here is the part I'm going to be talking about. And so this phase one here would more coincide with just before you start seeing the main convective blow up in the Indian Ocean. You see that the signal was initially very, very strong, but then once you got into the Indian Ocean component, it petered off really fast. So there's something a little unique about this particular MJO that was sampled compared to the one that happened in November, which is this green one here. There's a lot of unique things about this particular MJO compared to some of the other ones that have been sampled. So kind of diving into what's going on with that. And one thing that, again, looking at this role of vertical wind shear and moisture, this is what we're going to be looking at. This is from Kearns and Chen in 2014. And one thing that they were looking at is how does the influx of dry air intrusions into the central Indian Ocean essentially shut off the convection over the central Indian Ocean and help the MJO propagate towards the east. And so this is going upward in time. It's a little confusing, but basically, so you have this double ITCZ structure that's centering around the central Indian Ocean. That convection moves towards the equator, but now you're having this dry air intrusion from the south helping to essentially push that convection towards the equator. But then you get another dry air intrusion more from the west, and that starts to create these breaks in the convection. And eventually, you get a full intrusion of this dry air along the equator that helps to shut that convection down. So this part here, where you start getting essentially this dry air intrusion associated with the westerly wind burst, is one part that I'm particularly interested in. So if we look at the total precipitable water for this time frame, this is at the beginning of October, so before this MJO event began, you can see that you have high moisture associated with convection south of the equator. Now, at the initiation of the MJO, you see that central, the equatorial region being very, very moist. But then once you get towards the end and that westerly wind burst is getting involved, now you see that the total precipitable water has dropped along the equator, and now you might see some little vortices on either edge associated with the Rossby gyres associated with that westerly wind burst. So this is the precipitation trace for the three different time periods that were measured during Dynamo. this is the time period I'm going to be focusing on. So you can see that at the beginning of this, you had this massive outbreak of precipitation, and that it tails off as you go forward in time. So we're going to be looking, one thing I'm really interested in is what leads to this drop? What leads to this tail off? Is it just like, oh, well, there's dry air, so of course. Well, I think it's not that simple, right? So for a variety of reasons, when we go back to this, what the heck is on the radar, one thing that's really interesting about this is that we have a distinctive break between what kinds of precipitation is seen between the earlier part of the convective outbreak associated with MJO1 and the latter half. So in the earlier half, you tend to see a lot more just convective and stratiform precipitation. You get this strange thing called mixed precipitation, which is like a giant blob of stratiform with enhanced convective cells inside of it. Time period 2, you still get some of this stuff, but it's way more dominated by isolated convective cells. And at the very end, you start seeing squall lines. So what is the transition between time period 1 and time period 2? So the first thing that is noticed between these two time periods is that, in general, you just get a drop-off between all the different kind of precipitation types, stratiform, convective, uncertain or mixed, and isolated convective cores. So you get a lot more of them in time period 1 and time period 2, just overall. So that's, okay. I mean, so all the precipitation is being affected by something between these two different time periods. But another interesting thing, though, is that it really depends on what you're talking about. So this is a contoured frequency diagram by time. And so this is the reflectivity that's greater than 30 dBz. How is that distribution as a function of height and time? So what you're seeing here is that you have a pretty strong prevalence in both in terms of depth and in terms of longevity for stronger convective elements. So when you start getting above 30 dBz, you're talking about stronger convection, either intense stratiform or strong convective cells. So you're seeing a lot more longevity in these kind of systems. However, and here's the big but, the reason why there's this asterisk is because you see the depth of this. This is at the very end, and this is associated with that squall line. So there are perfectly powerful convective elements in this latter period, but they don't last very long. They're much shorter lived. So that was interesting. And we also have this, you see that in this image, we have this kind of periodicity of when these convective elements happen versus when they don't. This is the relative humidity associated with the soundings during that time. And one thing you see is that those two-day periods in those traces is associated with these intrusions of dry air in the upper levels. However, and here's the other however, you also start to see in the latter half of time period 2, you start seeing this influx of dry air in the mid-levels associated with the westerly wind burst. So there's a few different things going on, right? There's whatever this is, and the thing is that whatever this is, there's some ideas in terms of it being associated with gravity waves, and there's still not a lot of idea like what the heck this is about. What is this two-day periodicity about? But we're seeing it, just like everyone else. But the thing I want to point out, and this is where I say that dry air necessarily being a bad thing when it comes to convection is a little, right? And the reason why, this is the theta E, the theta E. So what you're seeing here is that you get a big drop in the theta E in the mid-levels in that latter period. If you have that much of a negative gradient in theta E, then you're starting to talk about pretty strong convective instability. So now suddenly, the fact that we're getting those intense, deep convective cells, short-lived, but there, starts making a little more sense. Now suddenly we start talking about maybe having a lot more convective energy than in these earlier time periods. So we had a lot more convection, but it's not as strong as this stuff. And as I mentioned, this period here, this is when the squall line showed up, is during this latter period. I know I'm running a little over, sorry. I'm almost done, I promise. So some of the other things we're doing, so we're looking at the ERA interim analysis, the reanalysis, excuse me, for the relative humidity data. And so one thing this is all my students' work, and so he took a average over this size of a box with the dot representing the center of the domain, which is where GAN is, the S-Polka radar is. And one thing that's really, really interesting about this is that you see that 2-day periodicity happening in the upper level relative humidity very strongly. This is the average over the 200 to 400 hectopascal, this red line. You don't really see that in the lower levels, excuse me. We're not down at the surface. This is the green line's the 700 and 925 hectopascal layer. That's a little bit more constant. You do get an oscillation here, but one thing you notice is that there's a big drop-off towards the end. Again, that drop-off is associated with the westerly wind burst. Another thing that he looked at is the increase in wind shear. So you see that the deep layer of shear is 200, 850 hectopascal, gradually increasing over the whole time period. You also get a small uptick in the low-level shear, again associated with the westerly wind burst here in the latter period. So we have this increase in wind shear. What is that going to do? Well, we do know from especially MCSs and squall lines rely on having some wind shear to form. We know this, right? And so essentially that increase in convective instability combined with this increase in wind shear is that basically setting up the conditions to be able to have more organized convection later on in the period. So the thing I want to wrap up with is talking, again, going back to that issue of stratiform. So the things that are interesting about this is that the dotted green line here is the aerial coverage of the stratiform precipitation observed by S-Polka. And the things that I want to point out is that you definitely see, and it's not that much of a surprise, you see an increase in the upper level moisture at times where you have large amounts of stratiform precipitation, which makes a certain level of sense. The stratiform is helping to dump particles and moisture into the upper levels. But one thing that's really interesting between the two time periods, though, this is the ice crystals for the earlier part of the period. This is ice crystals for the latter. You see a marked shift downward, both in terms of height and towards lower reflectivities in the ice crystals for the latter time period than the earlier time period. So we looked at all the other precipitation particles. None of them exhibited as much of a shift as these ice crystals. And so what seems to be happening is that these influx, these changes that we're seeing between the earlier time period and the latter time period seems to be impacting the ice crystal formation the most. The warm rain stuff doesn't seem to care as much. And one thing that is interesting about this is that this is the divergence from the ERA interim analysis. Again, the orange being the upper level, and then with the lower level is the dark red line. Now, it makes a certain level of sense that the peaks in stratiform precipitation align with times when you have increased mid-level convergence and upper and lower level divergence. That's just a classic stratiform profile where you have mid-level convergence, you got stuff going like this and stuff going like that, right? But what happens though if your mid-level convergence is increasing during those times and that's where all your dry air is coming from? What's that going to do, especially to your ice crystal formation? So these are the questions that we're exploring. And so that's why I have to say, like, the conclusions so far, right? This is all a work in progress and work that we're working to publish right now, is that I think we really need to reconsider when you're talking about shear or moisture or the lack thereof, they might not necessarily be bogeymen on their own. They may not have the impact that everyone assumes that they have. I think there must be much closer look into the impacts on exactly what kind of system that you're talking about. And the point of that is that the vertical moisture and vertical wind profile may affect different kinds of precipitation systems differently. And especially the more organized your system gets, it may interact with these things in a very different way than, say, an individual convective cell. And the final take home, especially in the tropics, it does seem that if you start messing with the ice processes in particular, that's where you start seeing the major differences. The warm rain processes, I mean, we get bubbling up a convection all the time. They don't seem to be impacted as much. It really does start to seem like the ice processes are more of what's important. So with that, I know I ran a little bit over. Sorry about that. I'll take any questions that you guys have.
Okay. Do we have questions in the from the audience? I guess people want to go to lunch. Well, I have actually two questions.
Okay.
One being, do you think the convection and interaction with the environment is different in different tropical ocean basins? Like, this is what we see in the Indian Ocean. Would it be different in the Westpac, in the Western Pacific, in the Eastern Pacific, or in the Atlantic, in the Caribbean? Or is it just more general?
You know, that's a really interesting question. I think I would say possibly, but for the reasons that, for example, the Westpac has, you know, copious amounts of warm sea surface temperature. You know, Eastpac, for example, has much stronger gradients in terms of both moisture availability. Your shear profiles are completely different. Some basins, like the Indian Ocean and the tropical Atlantic, have much more influence from interactions with air masses from land. So like the Saharan air layer and the Atlantic, the Indian Ocean has the monsoon circulation and, you know, influx of air masses from both Africa and from India. So I would say that I think what I'm saying is more universal in the sense that what playing field that these systems have to deal with is going to vary, but I haven't really seen anything, you know, now that I've worked with, you know, both stuff in the tropical Atlantic and with the Indian Ocean, a lot of these things still seem to be not the same, but, you know, that this idea that it's not as straightforward as this is bad or this is good. I think that still applies.
Okay, and then another question I had is, you're an observationalist. What do you want modelers, how can modelers help your research?
Oh gosh.
If you had a wish list, what would you want us modelers, well, I consider myself a modeler now, do?
Well, I mean, the one thing is, so the beauty of Dynamo and Olympics and the upcoming Relampigo, the beauty of those campaigns is that they have radars and things that can take samples over long periods of time. One thing that's really difficult about aircraft missions is that they are very snapshot in nature. It's very, very, very difficult to get evolution. That's where modeling has to come in. And one thing, I mean, I'm hoping to do is to work with modelers to help put my observations in context. You know, there's things like, especially the thermodynamic fields. You know, we get point measurements with the soundings, and it's nice when we can lay out this nice grid, but then there's time variability issues and all sorts of things. The models really can help complete the picture and put the observations in context that you just cannot achieve right now with observations. But the other thing is, and one thing I want to make clear is that I think, you know, observational work is extremely important because we see a lot of things in observations that there is no theory for. On the flip side, you know, theoreticians come up with lots of things that we don't have observations for yet. both of those approaches are valid, and we all have to work together to help bring those things together. So, you know, I'm an observationalist. I'm not in the service of a theoretician, and a theoretician's not in the service of observation people. So I do think there needs to be a lot more working together. And one thing I will say about Dynamo that was fantastic was that the modelers actually came out into the field. And, you know, usually for a couple weeks or whatever, but just to see what we were seeing in action. I think that's really, really important. I don't think there's enough of that. And I should probably sit down with modelers and see them think around with the model more too, right? So yeah.
Okay. Oh, yeah. Time for one quick question. Sharon?
So one of the things that struck me in terms of your observations and the intrusion of dry air in particular is it seems to me that, do you have any evidence of some kind of closed circulation that helped prevent the dry air from going into Nadine?
So that's one thing. So this kind of gets into that marsupial pouch theory. So that is one thing that's interesting, is that especially earlier on, one thing that probably helped Nadine be protected earlier, you know, like that 11th through 12th time frame, was that there was some indication that there was that closed circulation that would help insulate her burgeoning circulation. Later on, not so much, but then by that point, Nadine's own circulation itself was mature enough to probably provide some insulation. And so it's that idea of, especially in more mature storms, how do the rain bands actually might provide that insulating and, you know, that processing of external air to make it less damaging to a storm. Because one thing I actually forgot to mention about Nadine that was really interesting is that because of the shear and the asymmetric precipitation structure, all of that enhanced rainfall was falling right into the sal air mass. So there's a pretty decent chance that that air mass was being modified by Nadine's enhanced precipitation because of the shear. So that shear influence may have been helping in a weird way, right? So, yeah.
All right, so let's thank Deanna again. And Deanna will actually give another talk tomorrow, not a technical science talk, but a little bit more broader in general. And so if you're interested in that, I welcome you to come back tomorrow. I actually don't know the time. Is it going to be this?
I think it's the same time.
Same time? Okay. Yeah, so.
Same bad time, same bad channel. Right. Thank you.